Hello, everyone. Thanks for coming. This is the April webinar. We're going to talk about package units with thermal storage. But before we do, I'm going to give you just a, well, I guess you can say a quick commercial. I don't know if you know this, but a lot of folks think that what Abraxas does is we made a metrics software or option C software. It's used for, doing M&V for ESCOs, and some energy managers use it as well. But we also, or actually also, what we mostly do is energy audits and retro commissioning. That's our thing, especially in the hospital sector, but we do it for ESCOs, we do it for hospitals, we do it for universities. We do a lot of audits and retro commissioning all over the country and actually all over the world. Well, that's the end of my commercial there. But if you guys need some help, please come find us. And now let's actually really start with the webinar. Today, we are speaking with Ian Doebber and his twin. And the craziest thing is they don't even look the same. And they're going to tell you about package units and thermal storage. I'll give you a little bit of background. There was a solution about this with package units and thermal storage. I saw a guy gave a really great presentation at AEE West about 5 or 6 years ago. And it was really amazing because it was like they had made the package unit specifically for California and our outrageous TOU rates, because we're paying over, I think it's over $90 on peak. That is, if your peak your monthly peak corresponds with on peak, it's over $90 per kilowatt if you're on the certain rates like the E19 or E20. It's just obnoxious, and so their package units were set up so that you don't have to do any cooling during peak periods. It was amazing. I was so shocked. The name of that company was Ice Bear, and they're actually related to Ian, the twins company that they're going to tell you about. I met Ian at a trade show. We talked a lot about it, and that's why he's here. And so, Ian, why don't you introduce yourself and your twin? Uh-oh, we can't hear Ian now. Can't hear him. Try it again. No. Maybe the twins should speak. Oh.
Hi, my name is not Ian Doebber. My name is Dom Lempereur. We are not related. It's just the way we have signed up for this, registered for this webinar. I'm a senior energy engineer at Blue Frontier. I'm coming with over 30 years of experience in as a building consultant. Try to make building systems better, more efficient, as well as buildings performance. So,
why don't you introduce your twin while he is?
Yes. So my twin Ian. So he's a principal energy engineer at Blue Frontier, and he has been with Blue Frontier over 2.5 years, yeah, we are on the same team. He was the one person in actual engineering team to support business development at Blue Frontier, and I joined his team of one about 5 months ago.
Okay. Ian, do we have you on voice yet?
I hope so. Yes.
Oh,
how's that?
we do. Okay.
Oh,
let's get on with it.
Thank goodness. I need my nephew here to help me walk through this technology stuff. Okay, so real quick, Ian Doebber, mechanical engineer. Dom, thanks for walking through your background. I'll be quick. Started out doing design engineering for a company Era in San Francisco, California market for a long time, or a number of years. Then jumped into the R&D space. Was at the National Renewable Energy Lab, also now known as the National Lab of the Rockies, for a number of years, doing field demonstrations, emerging tech development, that sort of thing. And then I joined Blue Frontier 2.5 years ago. And Dom and I are a team of two in our energy engineering group. So quick, start with a thought experiment. Dom and I have been going to a lot of conferences, talking to a lot of stakeholders, and we were kind of came up with this internally. We just thought it was kind of flipping things on its head. So what if AI / this data center boom happened in 1902, and instead Willis Carrier commercialized the first modern air conditioner in 2023? And so think about how the energy markets would be freaking out even more given the difference in the type of load profile. And so with data centers, there is some flexibility when they do the training, when they're doing the inference. And whereas cooling, unless you tack on some sort of thermal storage, there's no way, I mean, you got to cool at the time that the building needs it. So segue into kind of what a load profile looks like. This is PJM, no surprise. When a building needs cooling, if there's no thermal storage, it coincides with all the other buildings needing cooling, and so you get these crazy spikes. So imagine our grid and how much chaos there would be if the rate of cooling installations was happening at the same rate of data centers, but it was cooling that was the new technology, not AI. So here's the peak, and so no surprise, here's California. That's 93% of the peak 500 hours happen in the summer. And then here's a correlation of the different loads for California based on the season. In blue is the temperature, and in white is the load, and you can see the extremely strong correlation there. So no surprise. So segue into, okay, we now know the grid's got problems, and kind of break that out, disaggregate that. So there's capacity. So DOE, and you hear other stakeholders mentioning this, Dom and I were just at the Edison Electric Institute, EEI National Account Show in Phoenix. Actually, Dom is still there, he's flying out later today. And they're saying the same thing. Data centers plus other loads is going to double the electricity demand very soon, 2028. That's only 2 years away. That's just insane. And you can see this is a recent report from JP Morgan, kind of aggregating from a grid perspective what's happening. Then we move over to the second problem, which is interconnection queues. And in some markets, the average time between a project request and actually getting hooked up to the grid is 3 to 8 years. So we have all this capability or demand, but there's a huge wait to actually get hooked up to the grid. The third problem is transmission build out. It can take a decade to permanent builds. And then the fourth problem is distribution. So this is down at the substation level. Many utility regions have been deferring distribution upgrades for decades, most notably very urban environments, think New York City. And now that infrastructure not only needs to upgrade to replace what was there, but now is being asked to expand to carry more load, like this doubling I was mentioning before. And so as an example of this, utilities and grids are getting desperate, and they're starting to throw money at the problem. And case in point, in New Jersey, they have this grid storage program where they're saying, bring your storage, we'll give you $300 per kilowatt incentive. I mean, in addition to the money you'll make by participating in the grid. So I'm going to pass now back to Dom.
Thank you, Ian. So as we understand, there's a grid problem, and what we see is really a solution that involves storage, both at the utility level, at the grid level, but also behind the meter, meaning at the building level. And there are currently technologies that are available on both, and we're going to focus now on what is behind the meter, what solutions we have. Next. So let's look a little bit at the history on how the grid have been upgraded since 2020. So what you can see is basically how much capacity have been added to the grid. Let's look at 2020. So the total of the energy sources that have been added to the US grid, I'm talking about the US grid, altogether, is around 32 gigawatt, right? And you can see that the leading technology in 2020 has been solar as well as wind. If we are focusing on the battery storage technology, you can see a big difference between 2020 and 2025, following the knowing that in year 2020 the battery storage was just close to zero, right? Very minimal. But 5 years later, it represents a significant part of that energy sources that have been added to the grid. So if we total the battery storage and solar, we're about 80% of those technology compared to the entire power generation technology. That's what it represents, above 80%. So let's focus now on what is at the building level, and just imagine an HVAC system, cooling system, that would have that storage capability. Okay. On the left-hand side, we have, just to give you an idea of the magnitude of the potential for this type of technology. Just looking at one unit that represents 20 tons of air conditioning, and assuming that the peak hours are between 3 and 9 p.m., you can see on the gray line being a traditional, let's call it traditional, direct expansion air conditioner, and compare it to a technology that is a Blue Frontier technology. We can see the potential of a reduction, at least at the peak time, of about 26 kilowatt. What does it mean to a local grid if not one unit but 400 units were actually installed? We will be talking in megawatts, in this case close to 10 megawatts of potential reduction. That becomes a very huge impact, very large impact to the grid. So as Ian explained, it takes a lot of time, many years actually, to connect new loads to the grid, directly to the grid. But the solution that we're going to talk about is really a system that every building uses, which is a cooling system, dehumidification system, and in this case, Blue Frontier have that storage capacity. So we understand that the benefit to the grid, if there is a technology that could be installed so that the peak demand are going to be reduced. But there's also, in order to have that, behind the meter technology being installed in buildings, we obviously need the vetting from the decision maker, let's say the building owner. So here is a graph that represents the utility rate and how they have increased over the past 5 years. Starting again from 2020, which is the base, basically in 5 years, the average nationwide utility rate, electric rate, have increased by 40% in 5 years. What is also very important to understand is the first few years, let's say until Q1 2022, that increase in electric rate was following more or less the inflation. But after this time, mid 2022, there is definitely a divergence, right? And the price of electricity right now, again, we're talking about average, it could be very regional, you know, but on average, there's now a disconnect between the rate of inflation and the electricity price. So we believe that a building owner should be very interested in looking into technologies that can actually save. And the focus of the unit from Blue Frontier is really based on looking at a utility tariff and compare also how the consumption rate in dollars per kilowatt hours vary over a season, mostly winter versus cooling season, and also over a 24-hour period of time. Some of you may be familiar with those tariffs, using it, you know, analysis and so on. But what is important, although there's a lot of very colorful, you know, graphs here and tables, but in short, we see a huge difference between, you know, in this example, we have period 1 through 6. But looking at period 1, which is basically an off-peak period during the winter, and we compare it to a peak period in a summer, we are talking about a factor of 3, close to a factor of 3 in the rate, right? So, and there's also a big difference over a 24-hour period over, you know, in a summer. So that's for energy time of use charges. In a PG&E territory, a utility territory in this case, and looking at the demand charge, and John was mentioning about close to $90 per kilowatt. This is what is being reflected here. And again, the delta, the differential between off-peak and on-peak is significant, and therefore there is then the potential for savings. And this is how we're going to we're going to do it. If you want to move to the next slide, please, Ian. So we believe that the time of use and optimizing the tariff, the time of use tariff, can really help reducing the high demand rates. And now we'll be talking about 2 components of the solution. First is to have energy efficiency, to provide a technology that provide just a better performance from an energy perspective that will generate those savings. So we will be talking about working on the consumption side, right? That was on the left side of the previous slide that I showed you. Now we need to be the most efficient as possible, is to add also the load shifting component, meaning that we'll be using more energy in off-peak time to reduce as much as we can use power draw during the on-peak. Okay, and the combination of the 2 is a solution that we're presenting today. So what does it mean in terms of efficiency and the performance of a Blue Frontier unit, and how it compares to a baseline? In this table, the baseline is basically a direct expansion DOAS system, cooling system, a dedicated outside air system, DOAS. And we measure that in terms of IEER, which is how much a kilowatt hour is necessary to provide a certain amount of cooling, okay? Looking at the baseline and compare it to the Blue Frontier, you can see a factor of about 2, right? So meaning the Blue Frontier in a standard run mode is about twice as efficient as a baseline GX unit, right? That complies with the ASHRAE 90.1. You can also compare the Blue Frontier in a standard run mode to a control strategy that includes a storage, right? And in this storage mode, basically we reduce the demand as much as possible, and therefore we have extremely high efficiency, because during that time we are still using, again, small amount of kilowatt hours of electricity, but the same amount of cooling and dehumidification. If we are looking now at the bottom table, we are now looking at how efficient a DOAS system could be to dehumidify the air. And now we're talking about a metric that you might not be very familiar with, but it's ISM or RE2, which stands for Integrated Seasonal Moisture Removal Efficiency. So same thing, it's dependent to the cooling. So how much kilowatt hour does a system need to remove moisture from the air, right? So that's how it's about. The baseline is about 4, and the Blue Frontier is about 2.5 more efficient than the baseline. In a storage mode, again, we are not using as much a kilowatt hour. There's a few slides that are going to explain how, but we have an extremely high efficiency rating. So how does it look on a graph, right? On a 24-hour hot day, summer day, looking at the graph, again, in gray is the baseline, in blue is the Blue Frontier unit. You can see between the hour of 4 and 9 in this example, this is the on-peak hours where the most expensive. The unit will continue to provide the comfort to a space without using as much electricity. In a dotted line is basically the same unit, Blue Frontier unit, working without a storage strategy. Okay, so again, two things. The delta in terms of kilowatt, but also altogether, if you're looking at the area, the gray area versus the blue area, that represents the savings in energy consumption, about 54% in this case.
Yeah, so now we're going to jump into the package units, the package unit itself and its specs. And so this is the unit, what it looks like. And so what you can see on the left here is the conditioner core, which is essentially, think of it like a fan coil unit. So this is the air being blown through. You can see the fan there, number 2, being pushed through the heat exchanger, which is the number 3. And that is then pushed into the supply plenum, number 6, and then delivered to the building. So that part of the system is doing the cooling and the dehumidification. The liquid desiccant energy storage module is there on the right or middle of the unit. This is essentially a 300-gallon tank of desiccant. And so where the storage comes from is the ability to have that desiccant concentrated at 100% state of charge, which is essentially 70 to 72% concentration. And then going down to a 0 state of charge would be about 58% concentration. And so that's the desiccant being pumped into the heat exchanger number 3 to give the cooling and dehumidification part of the process. And then the final subcomponent of the system is the regenerator, which is all the way on the right. And I'll jump to the next slide to kind of give a more zoomed in view of the regenerator. So this is kind of shifting the perspective from the viewer to the end of the unit, and we're looking into the regenerator. Essentially, all this is a heat pump running in heating mode during the cooling season, so a little bit non-intuitive. And we're pushing moisture out of the desiccant. So in other words, the desiccant grabbed water from the air to provide the cooling that was going into the building. now the desiccant is diluted. So we need to push the moisture out. So the desiccant comes in here, we heat it from the hot refrigerant, leaving a scroll compressor. Then the hot desiccant sees hot air that we're also heating. The moisture is being transferred from the desiccant to the air, and then we're simply dumping that air outside. So because we actually run the unit as a heat pump in heating mode during the cooling season, we actually become more efficient the hotter it is outside. And what we've seen, because we do monitor the regenerator efficiency real time through our IoT system, we see about a 15 to 20% increase in its efficiency as the temperature goes from around 80 degrees to the low to mid 90s. So it's a dramatic improvement in the efficiency of the system at hotter temperatures. We included this slide. This is a link to a way to share the model, and hopefully I'm not going to break this here because I've already got a bad track record, but hopefully I can. You guys, Dom, am I showing the 3D model?
Yes.
Okay, great. So here is a way that you can go to this link and rotate the unit around, kind of zoom in to see the different components of the model, and you can click on each one, and it'll describe what's going on with each subcomponent. Okay, so I'll jump back to the presentation here. And not to focus too much on this, but if there's questions, we can. This is just a basic schematic of how the system breaks down into the three main subcomponents. So we have on the right-hand side, the heat exchanger where outdoor air is being brought in, cooled and dehumidified, and then supplied to the building. Decoupled from that is the 300-gallon liquid desiccant tank, which is our energy storage. And then on the left-hand side is the regenerator, which is used to reconstitute or reconcentrate the desiccant. And so this 300-gallon storage gives us the 6 hours of storage that we are referring to. And so the specifications, from a design engineering perspective, is the rated tonnage size is 20 tons. The applications, we've been talking about DOAS, but we can also be a mixed air rooftop unit. We've been calling this the super RTU because the unit is so effective at dehumidification, it can handle much higher outdoor air ratios compared to conventional rooftop units. So for instance, a typical RTU is anywhere from 10 to 25, maybe 30% outdoor air ratio that it can handle and still meet its supply temperature set points. With our unit, we can go up to 100%. So it gives a lot more flexibility for applications. For instance, you could put a rooftop unit serving a cafeteria of a school and pump a lot more ventilation air through that, as opposed to a conventional rooftop unit where you might need 2 rooftop units to do the same amount of ventilation. Energy storage-wise, we benchmark ourselves against what the DX-DOAS system would have used over that 6 hours. And so based on what we're seeing of a 25 to 35 kilowatt average kilowatt power reduction on average over 6 hours compared to a typical DX-DOAS system, this translates to about 150 to almost 200 kilowatt hours of what a lithium-ion battery would have to provide from a storage perspective. And then the final metric to point out is the electric power during discharge. So here we have 1.5 to 3 kilowatts is all the power we use during our 6-hour discharge event. And that's just to power three fans and a small desiccant pump. So talking about third-party validation, The main one that we have, I'll touch on some other ones that we have as well, but this is kind of the biggest pilot that we've done, which was the CalNext, part of the CalNext program. It was done in Southern California Edison territory. It was installed on a large grocery store in Los Angeles area, and you can see the picture in the lower right. There's a link to the report on the ETCC website, and it was third-party validated by the Western Cooling Efficiency Center, great folks out of UC Davis, AESP, and Energy Solutions. So the main takeaway from the report is, as Dom was mentioning, the need to have both energy savings and peak demand reduction. So on the energy savings side, you can see that the savings was anywhere from 48 to 69%. And so we essentially extrapolated the measurements from the site in Los Angeles to do 8760 modeling of our unit compared to a conventional DX-DOAS system in different climates. So we have Riverside, Sacramento, and Palm Springs. What's notable here is that because our unit uses indirect evaporative cooling as the way to sensibly cool the air after the desiccant, we actually become more efficient in drier climates. So even though our unit, one of its main value propositions is the ability to dehumidify air in extremely humid climates, we actually become more efficient, or we save more energy the drier the climate. And you can see that here in the table, like going to Palm Springs, which is extremely dry, the impressive 69% energy savings. Now flipping over to the energy shifting side, from 4 to 9 p.m. during California's peak, our maximum power draw was 3 kilowatts. So again, that's the 3 fans and a small liquid desiccant pump. That was the only thing that was running, while still providing the full 20-ton cooling capacity of the unit. Compare that to a DX-DOAS. Its maximum power was essentially 25 kilowatts. I won't go through each one of these because of time, but these are the other third-party demonstrations that we've done. So the Westover Air Reserve Base out in Springfield, Massachusetts. We've actually done a couple demonstrations with Department of War through the ESTCP program. That is third-party validated by the National Lab of the Rockies. We did a Waffle House demonstration with Georgia Power. We're about to kick off in beginning of May a demonstration of Valencia College, and this is with Duke and DOE. DOE is working with Oak Ridge National Lab to do the third-party M&V. And then we have a mixed air, it's a super RTU application with Florida Power and Light. That's ongoing M&V, no reports yet, but that'll be wrapping up later this year. And this is just a quick showing of the different units in different locations. And we did receive a 2025 R&D 100 award, and also we got the product of the year under the sustainable solution category at this past AHR, which was a great win. And so I'll pass this. Dom, do you want to cover these slides, or?
Absolutely.
Yeah.
Yes.
Yeah. Okay. Go for it.
So yes. Yeah. Thank you, Ian. So let's look at how we estimate the savings. As Ian explained, there's a lot of variation based on the climate, but also with a building type, but also the utility rate that affects the dollar savings. So the tool that actually Ian developed is a hourly model that compares the baseline, which is a conventional DX cooling unit, to the Blue Frontier. So we calibrated basically some of the numbers or units that we are using, specifically the airflow per unit, as well as set points such as dry bulb and dew point, and the savings that we observed and confirmed in the field actually were used as a feedback to make our model for the Blue Frontier more accurate. So to really compare apples to apples, we want to make sure that those parameters, again, the airflow, the dry bulb dew point of 55 in this case, are the same on each side, right? So next, oh, well, just 1 second, sorry. So you can see on the that we're looking at what are the parameters we're looking at, right? We're looking at the climate using the TMY3 that is local to the building, right? Looking also at the equipment design, which is what you're looking at now. Also inputting what is the building schedule, when does the cooling system operate, in what time of the year, what day of the week, etc., etc. The input is also the utility rate, and we are using OpenEI, which is a tool that was developed for the GSA for solar applications, but nevertheless have a lot of information on most of the utilities in rate and tariffs in the country. So this is, in short, it will take a few hours to go over this tool. If we can move to the next slide, here are a few examples of the report coming out of this tool. This example is for Los Angeles, and basically in the report we have how much savings have been generated and the difference between a Blue Frontier consumption and a baseline consumption. Again, at DX DOAS 90.1. And we look at the savings and as well as the peak power reduction, and we translate, because of the utility rate that we are inputting or looking at, we translate those kilowatt hours and kilowatt into dollars. In this case, if we add those energy savings and the peak power savings, we come up with a total. Ian mentioned that how we do cooling and reduce sensible cooling. We use a water, in the process, right? So we're using city water. We have a connection, and we also, just to be fair in our calculations, saving calculation, that we are deducting the cost of water, right, or the water bill. Now, a little bit, just to give you a little bit of information about the magnitude of the water being used. In this case, in Los Angeles, for a 20-ton unit, it's about 44,000 gallons. That represents annually, right? That represents also the annual consumption of a household that has 1.5 people. Average US, we did the math. So it's not a huge quantity of water. There is some water, but it's relatively minor compared to other technologies, basically. Next. So as we said, the tariffs that we're using locally, the climate has some impact on the calculation. Looking here at Sacramento, the energy savings reach close to 70%, which is significant. And we translate that again in dollars and deduct the water bill. One more example, in Miami, in this climate, hot and humid, right? We see that the energy savings are a bit less than in Sacramento, for instance. However, what remains relatively constant is the peak power reduction, right? And one of the relatively constant. What is constant is the fact that how much power the Blue Frontier actually uses during the on peak, and we are typically, in most of our units, right, we have a reduction on the on peak hours of about well over 90% reduction in peak demand. Right? In this case, you will see, however, that the water usage is higher than in some places in California. Again, that's another example of a report from our tool.
And just, I know we're getting close to time, so we'll fly through the rest of these and then hopefully have some time for questions. So we talked a lot about peak demand reduction, energy savings, kind of the financial fuel for that ROI, which is, so critical for ESCO projects, performance contracting, and just really any project for that matter in our HVAC industry. But we did want to talk about the comfort and the ventilation benefits of the unit as well. So this is, from a comfort perspective, this is the cooling of our system at the Westover Air Reserve Base. It's in Western Massachusetts near Springfield. I don't know if you guys people remember, but if you were in the Northeast, it was awfully hot there at the end of June last year. These sort of freak heat waves are starting to become a little bit more frequent, unfortunately. And so what we saw was the outdoor air conditions just blew away the ASHRAE design conditions. It got into the hundreds, and not only did the dry bulb increase, but the dew point actually went up quite a bit as well. So we got to the low 70s dew point, which is very high and uncharacteristic for that part of the country. And so in the red here, we see that the outdoor temperature, as it made its way through our heat exchanger, was brought down to space neutral. So this is a DOAS application. We were serving a bowling center. And so we brought the air down to 70 degrees Fahrenheit. And then we took the outdoor extreme high dew points and brought those down to around 55 dew point. What ended up happening, we found out from the operations team at Westover, was the bowling center was the most comfortable building on the base. And so it formed kind of the hangout area for a lot of the personnel there during the week, and the heat wave lasted like a week. So it's kind of neat to see how the unit helped those folks out. And then switching over to ventilation, this is an element that's not unique to our system. There are a lot of fans, I'm sure a lot of you have seen this kind of evolution in the fan world, but more sophisticated direct drive ECM fans, fan motor systems are coming now with what's called a piezo ring. And essentially all this is measuring the static pressure between the suction of the fan and the inlet nozzle. And so this is a nozzle flow measurement, which is very accurate. And so our fans use this. And so we're actually controlling our fans to CFM. We can always switch to static pressure control for conventional systems, which we are doing in a few sites, but we typically like to control the CFM because that's what the customer cares about. You're providing ventilation to the building and to meet ASHRAE 62 requirements, 62.1 requirements. But then this also opens up opportunity to another powerful aspect, which is regard to M&V. And so being able to measure CFM accurately to plus or minus 5% is the spec we've seen from like Rosenberg and EBM PAPS. Although we've done comparisons to lab grade nozzle flow measurements, and it's usually better than that. It's usually around 2 to 3% accurate. And so that, from an M&V perspective, is extremely fantastic because you can actually monitor not only the airflow, but if you're measuring the inlet conditions and the outlet conditions of the air, you can quantify capacity real time. And therefore, we monitor power on our unit. So by knowing the capacity real time and knowing the power draw, we know real time COP or MRE or whatever your efficiency metric is, which has been fantastic for monitoring perspectives. Product roadmap, I'll touch these real fast. We have a split system later this year. This is the ability to have a central regenerator, which is about 75% of our weight, which is mostly that 300-gallon tank of desiccant. locate that on the ground or put it on over a column for a structurally constrained roof. And then the only thing you would have to pipe between the regenerator is 3/4 inch lines that carry the desiccant to the conditioner. Of course, you also have to have water going to the conditioner as well. But this is the ability to have one central regenerator, which is the unit there on the right, serving multiple, I call them head units, which is essentially just the fan and the heat exchanger. We call it our conditioner. And you would have those located in different locations on the roof. Then there's also the ability, we're working with GTI outside of Chicago to look at waste heat applications. This is the ability to get rid of our regenerator completely, or say to compress the heat pump inside a regenerator and just use waste heat. We don't need very high grade heat. Our heat pump typically operates at 125 degrees Fahrenheit. So if the on-site application had 125 degrees Fahrenheit waste heat or more, or even just in the high 90s, we can at least preheat the air and offload our regenerator. So there's a lot of exciting opportunity there that our product team is looking into. And just to kind of nail this home is that our regenerator energy use would go to zero. And so our current 47% energy savings in Orlando would go to 86% annual kWh savings. So with that, that's the end of our presentation. John, I pass it back to you.
Yes. Can you hear me?
Yep.
Yes. Okay. Yeah, I'm going to start with a couple questions of mine. So I noticed that the studies only one showed, maybe one, but most of them just showed kilowatt and kilowatt hour savings. But the thing that I was most impressed with was not kilowatt hour or kilowatt savings. You can just buy a super efficient package unit and get that. What I was most impressed by was money savings by avoiding the time of use, the high on peak rates. And your studies didn't show that. But I guess, yeah, that was just a comment. But my question though is, what kind of payback, from the units you've implemented, what kind of payback do you get in like California, New York City, New Jersey, or Ontario? Do you have any cases, and do you have any numbers you can throw at us?
Yeah, great question. And I was hoping you asked that. So if you don't factor in rebates from the utility or the ITC, which is something you definitely wanted to touch on, the investment tax credit with the IRS, we're seeing about a 4-year or less simple payback. Our unit has a premium compared to a code minimum DX DOAS from another manufacturer, but because of those substantial dollar savings, particularly in California, but as you saw in Miami, places where there's a lot of hot heat and humidity too, we see at 4 years or less simple payback. But then what's interesting is when you, if we're working with a customer that either can take the investment tax credit themselves because they have tax equity, or we're able to do some tax, offload it to another tax equity entity for like a nonprofit, which is feasible. And we're working with some financial institutions that do this. Then the unit is actually less expensive installed costs compared to the conventional unit, and it's because of the storage. So because of the One Big Beautiful bill that passed, that nixed a lot of the renewable energy, wind, solar, what survived was energy storage. And it wasn't just energy storage for batteries, but it's also thermal energy storage as well. Mm-hmm. So this also applies to CalMac, to SunAmp, there's other thermal storage systems. And those investment tax credits are extremely substantial. So they start at 30%. But if you get the made in the US credit, which we do because we manufacture majority of our equipment in a combination of Illinois and our headquarters in Florida, we're at a 40% minimum. But then if you're in a socioeconomic region, that can jump to 50%. And the other element that's really key there is the percentage does not only apply to the material or the piece of equipment itself, it applies to the installed cost. So DOAS, as we all know, the cost of installation of labor, materials, ductwork, you name it, has become astronomical since COVID. And so the installed cost of these DOAS systems is anywhere from close to 100,000. We've seen as low as, I think, 85,000 was the lowest, depends on the region, up to a little over $200,000 just to install a system. And that's any DOAS system. That's the crane fee, the labor, all the duct materials and things out, not just the equipment itself or the unit itself. So the ability to apply that 40 to 50% ITC tax credit to both the unit cost itself and the install costs means we're actually less expensive. So the payback is immediate for those types of customers.
Okay, let's see, another question for me, and we've got a lot of questions, so if you can make your answers shorter, it might be better. I mean, not what you said was really valuable information, but just so we can get them all in before people have to take off. So you said that your unit is more expensive. Of course it is. It has more technology in it and all this other stuff. But for an equivalent super efficient model of a package unit, what kind of additional cost is it? Is it 10% more, 30% more?
20 to 30% more.
Okay.
Versus a code minimum unit.
Okay. Wait, I didn't understand that. 10 to 20% more over what?
Sorry, I said 10% incorrectly. 20 to 30% premium over a code minimum unit for the unit itself.
Over a standard efficiency unit, you're saying? Oh, okay.
Correct.
Well, but you have competitors that aren't using thermal storage, and they also have a premium. And isn't their premium about the same? So is yours about the equivalent price of a super efficient, package unit, or is it going to be more?
I would actually have to look at numbers. We've gotten pricing from like code equivalent unit, but I would say on par to 10% more compared to a premium efficiency unit that, but that does not have energy storage, and still doesn't have I think the premium efficiency is anywhere from 6 to 7 ISMRE2. That's the efficiency metric, whereas ours is 10.5. So I probably shouldn't use the word premium efficiency. It's a high efficiency unit, but it's still, it's still about 30% lower efficiency than our unit.
Okay, here's the next question. How would this be economic in Ontario, where we have a summer peak, but only for June to September, where we can get demand response or a custom incentive to lower peak?
Dom, do you want to cover that?
Yeah, no, absolutely. Indeed, right, when the summer is shorter than other geographies, right, it definitely, it logically affects the payback, right, because we have a cooling and dehumidification system. Now we're talking about the tariff. There was also a reference to demand response, and so this is, the unit, the Blue Frontier unit is a demand response, and we're working on demand response capability now, and so there's also this way to have additional revenue streams through demand response, and a different demand response options, right? Emergency and the more regular demand response. So additional revenue streams as well for the building owners are also available through our system.
Okay. Next question. Is this intending to replace ice storage tanks, supplement them, or serve a different customer base?
It would be the latter. It's a different customer base. And John, as you pointed out, when we first were talking about this presentation, because this is a package unit, it's all in one box. This is going after the small and medium commercial buildings that are just too small for a CalMac, an ice storage tank, don't have the real estate, that sort of thing. So we're going after a different market.
Okay. Do you have any case studies you can share or active machines in the field?
Yeah, the CalMac study, but we can send reports over from the other M&V studies to take a look, like the Westover one. Yeah, we're happy to share all that.
Okay, yeah. So if you guys don't know how to get a hold of, do you have your email address? Do you have a slide with your email address here? Or if not, they could just email us at webinars and we can pass it on to the twins, and then they could get you back. Let's see if they got one here. No. Okay. No email. So just send to webinars@abraxasenergy.com. Say I want some case studies, and I'll pass it on to Ian, and they will get back to you on that. Okay. Next question. Can the unit heat as well, or is this just for cooling? Such as, could this be used in a VAV reheat system? That's interesting.
Great question. So right now, today we're cooling only. But in Q1 next year, this is what our product team has been working most hot and heavy on, is a cold climate heat pump capability. We're working with National Lab of the Rockies. So right now, we're cooling only, but early 2027, we will have the ability to do a cold climate heat pump, which means 70% of the heating capacity down at -15-degree outdoor temperature, which exceeds the CEE requirements for cold climate heat pumps.
Okay, what is the filtration rating on the unit? Do the filters see any of the moisture gain? Could you use electrostatic or magnetic filters?
So we have, great question. We currently use MERV 8 pre-filter and a MERV 13 final filter, and those are upstream of the process fans. So as soon as the air is brought in to the unit, it goes through the filters, and then it sees the fan, and then it sees the heat exchanger. So we are filtering that air. We haven't. I mean, that would be an interesting. If you're able to email John, and then we can set up a call to talk more about that. We honestly have not dug too much into more advanced filtration, but it's something we certainly can look into.
Okay, this one's really interesting to me. The thermal storage is desiccant based and is completely latent heat absorption. Are there application guidelines for the various climates? Wait, we're still going, so don't answer yet. For example, the US Southeast, where humidity is king, versus the Southwest, there's a latent low heat desert. My assumption is that the applicability would be lower in low humidity environments, but I may be mistaken.
Great question. It depends on the value prop of the customer. As I was mentioning before, the energy saving, because at our core we're indirect evaporative cooling. So essentially, think of it as we are a liquid desiccant enhanced indirect evaporative cooler. Meaning that we first dry the heck out of the air, and then we run it through an indirect evaporative cooler. So because the indirect evaporative cooler is at the core of our capability, you can leverage all that energy savings. It becomes more apparent in drier climates. So as I was showing in Sacramento and Palm Springs, which are very dry climates, our energy savings goes up to about 70%, because we're still giving cool, dry air, but we don't have to dehumidify it as much with our desiccant. And so the energy, or kWh savings, as well as the kW reduction, increases in the dry climate. So the main way to answer that question, as I say, is if you have an application or just want to see an example, send us an email. We can get on a call, or we can just send you the output of that model, and you can see the actual dollar and cents associated with that application.
Okay, it's another one. Seems like we can't readily go down in size due to economy of scale. Do the units come in larger sizes, or do we have to look at ganging units together to get higher tonnages?
Yeah. Dom, do you want to take that one?
Yeah, no, yes, absolutely. So at this time, we are the model that we are offering is a 20-ton, and this is the application that we believe is the most common. But for larger buildings, we will have to gang those units to the ventilation requirements.
Okay, so I spaced out on part of that. So you said you make 20-ton units. You don't make 5-ton units. It's just 20s. That's all you're doing right now?
Correct. It's just, yeah, it's
Okay.
just that model, that size, right?
Okay,
Yeah, that
got it.
capacity.
Okay, is this equipment packaged? I think we know that answer. It's yes. Or can it be used with existing chill water loop? I think that answer is no. Is that correct?
So Dom and I are actually working on an application guide to touch on exactly that. So we would not need any chilled water, but we feel like there's an opportunity there. We've done a lot of Department of War, DOW bases that have had issues with air-cooled chillers, with oil fouling and things like that, where they're actually not able to meet the chilled water set point of, let's say, 44 Fahrenheit. So they slowly float up. It gets worse. It gets hotter outside, and as a result, the air handling units downstream are unable to hit their discharge air temperature set point, mainly on the dew point side. And so you have humidity issues, and this is like a serious issue that the DOW is dealing with. So we feel there's an application there where we add our unit, which doesn't need the chilled water, where we enable the downstream AHUs. Either we duct into their outdoor intake like we did at the grocery store for CalNext, or we supply separate ductwork into the space like we did at the bowling center at Westover. And either way, we are maintaining that 50, it can go down to 50 dew point supply, or 55, whatever the case may be. And then those downstream AHUs can mean that they can still hit their discharge air temperature set point and dew point set point. And you don't have to rip and replace the chiller. So that's one of the applications we're working on right now.
A question: do you have, or are any ESCOs working with you now? Are any using this as an ECM?
We are talking with several on projects, but we have not deployed one with an ESCO as of today.
Do you know if any have been presented as part of their performance contracting proposals? Do you know if they've gone that far?
2 of them have, yeah.
Okay.
In Florida.
Okay. How susceptible is the unit to water quality issues? Much of California has hard water that typically destroys traditional evaporative coolers in 2 to 4 years, significantly shorter than their stated life. How's that going to affect your units?
Yeah, great question. So we have a salt dispensing, it's a water softener that we deploy like the unit that we have at the grocery store in Los Angeles has a water softening. So we filter the water, and then we soften it as well, and that's all automated.
Is the water use evaporative loss, or is this fill and then drain or blow down? Can you get a sewer credit for not sending water to the sewer or not?
Yes. So that water usage that Dom covered, that the model calculates, includes, there is a little bit of blowdown. So we flow today, we're on the conservative side, we flow an additional 30% above what we evaporate. And so 30% of that water usage is going to the sewer. Okay. We have not applied for a credit. That's an interesting idea. If you want to email us, and definitely would love to have a conversation about that. That's something that we just haven't done yet.
I'm surprised the ESCOs haven't, because that's usually something they look for is, cooling towers waste, all this water evaporates. So why pay for a sewer bill for that? That's very common. Okay. What is the difference in total weight between a baseline unit and the Blue Frontier equivalent?
Yep. So our unit does weigh more. The full package, we're about 8,000 pounds. whereas an equivalent DX-DOAS system is anywhere from 3,000 to 5,000, depending on if you include an ERV or that sort, wheel. So we do have a weight, additional weight requirement, and that's why we are putting out the split unit later this year to deal with that. What we found is 90% of the projects that we've both installed and also are in the works have been able to move forward despite, using the existing roof. It was just a matter of siting the regenerator over the column, or the unit over the column.
Mm-hmm.
And so with the split unit, we know we're not going to address everything, but we hope to address most of those weight constrained projects where the regenerator can be put over near or over a column, and then you run the 3/4 inch line of desiccant to the different head units.
So if an ESCO is going to implement these, or is going to recommend implementing them, they probably should have a structural engineer look at it first. Does that sound wise?
Yes, and we provide that turnkey. I mean, of course, if ESCO has a preferred structural engineer, happy to work with them as well. But we've hired 2 engineering firms that we cover the costs to do the structural analysis.
Okay. Can it be integrated into the current BMS?
Yeah, great question. So we use Distech conventional. It's a BACnet native controller, and so we can do BACnet, we can do Modbus, and we have a whole kind of a IoT integration summary that we can provide that shows the points that are available that can be pulled in, both read and write. So that's very straightforward.
Okay, since you're using a heat pump, are there temperatures, outside air temperatures, at which it cannot operate?
Below, I forget the exact temperature, but I think it's like below 40 degrees. When it's like below 40 degrees outside, our heat pump, because the suction pressure gets too low, but at that point you wouldn't need cooling anyway. You would just go to economizing.
Right, because it's a cooling unit. Right.
Cooling only unit. On the high side, the hotter the better. So there is no limitation on the high side for our heat pump. And of course, with our cold climate design, we are addressing that. We are using a different type of scroll compressor that's more geared towards heating operation, because we're always going to be running that heat pump in heating mode, whether it's the wintertime or the summertime.
What are the O&M costs and frequency?
So it's a typical O&M activities as a standard DX-DOAS with filter changes. The only additional one is the water filtration, and then that salt, that salt tank where water hardness is an issue. So the only thing additional beyond typical PM activities is the water side of the unit.
So you don't have to change out the desiccant or anything like that, ever?
No.
Okay.
No, it's a closed loop. Yeah.
What are your production capabilities?
So we're manufacturing 100 this year. As I mentioned before, we have manufacturing in Florida and Illinois, and then next year's target is 1,000 units. So, those are the numbers.
Okay. Yeah. So next question is: are they in mass production? Or are they still being produced as a custom request? I mean, you're just producing them and then selling them. You're just putting them on the shelf if need be. Is that correct? You're not waiting for a request or an order.
Yeah, that's right. We have a storage facility, and worth noting that we are a 12-week lead time or less. So I know that DOAS systems in general are struggling right now with, or I guess a lot of HVAC equipment for that matter, up to, I've heard crazy stories of like 52+ weeks to wait for a unit. Because we are pumping these guys out, but 40 units this year, we are 12 weeks or less. So the timing for us is beneficial.
Okay. Do you have a calculator that could be used to calculate the energy and cost savings for different locations? That would be really useful for energy engineers. If you had something online or.
Yeah, that was what Dom showed, the web app. So we just transitioned, we're wrapping up internal testing of it. It wasn't a spreadsheet, but it's now into a web form. So we would provide that, and it could be self-served by engineers. So you could run models for whatever you needed.
There it is.
Different airflow rates and things like that. So you would select the TMY3 data, the climate you wanted. We provide all that in our database, and you can self-serve.
Perfect. And so if they just send us an email at webinars, we'll ask you, we'll pass to you, and then you can show them where you can send them a URL. Okay. Do you have the capacity to handle larger orders if working directly with an ESCO? I mean, can we ask you, let's see, what is this? This is April. What if we wanted 200 of these units by December? Can we get that?
No, definitely 100 units this year. But I would say email us, and we can always see what we can do, partnering with other manufacturers. We are talking to another manufacturing plant right now, so that's in discussions. But yeah, I would say email us and let's talk.
Any last words before we finish?
Just one thing to mention, we're actually working with the company called Big Ladder Software. It's one of the kind of preeminent energy modeling companies out there. And so we're actually going to have our unit in Energy Plus with a how-to guide by the end of May. So in addition to, so we can send you the ROI tool spreadsheets today, but then come May for, wanting to model it in your other applications, it'll be available. And so reach out.
Okay, and let's see what's left. I think that's it. Thanks, guys. Thanks so much for presenting. And as everyone, if you want slides, or if you want to contact Ian and his twin Dom, please just email me at webinars@abraxasenergy.com, and we will pass it on. Thanks, everyone. Thanks for coming.
Thank you for the opportunity.
Thanks, all. Thanks for your time. Thanks, John. Thanks, Tyler.